Professor Jeffery Herrmann, and he's a professor of mechanical engineering at the Catholic University of America. And Dr. Herrmann grew up in Plant City, Florida, and earned a degree in applied mathematics from Georgia Tech. He received a PhD in industrial and systems engineering from the University of Florida. He is also a member of the Society of Catholic Scientists, ASME, and IISE. His research interests include engineering design, decision-making, and meta-reasoning in robots. Welcome.
Thank you. Thanks for inviting me to be here, and I'm very pleased to be here. Am I in the right spot now? Okay. And one technical question before we get started. This thing is connected to what?
To computer right over here.
Okay, great. In a little bit, I'll want to bring up another website, but for now, you can just look at this beautiful picture of me. So you can tell. You heard that I was born in Florida, and then I went to Georgia Tech, which is in Atlanta, Georgia, and then I went back to the University of Florida. So I spent like the first half of my life where it's nice and warm, and then I moved to Maryland. It's not so nice and warm, especially this week, right? This is like the worst weather, the worst, coldest weather I've ever had here in Maryland, in my stay here for over 30 years now. But so I'll just tell you a little bit about how I got to where I am, and then about a couple of things that I'm doing. Okay. So when I was growing up in Florida, I went to the local elementary school, and we called them junior high schools back down there, not middle schools. But anyway, I really liked math. Math was my thing. I really liked math. I remember spending one summer reading the Algebra 2 textbook because I wanted to get ahead on Algebra 2. That's a really nerdy thing to do, but that's what I did. I just really liked math. So when I went to college at Georgia Tech, of course Tech is a big engineering school, right? All the different engineering majors, wonderful place. But I was not interested in being an engineer. People asked me, like, what do you want to study? And all I knew was that I was really good at math, okay? And so I was like, well, I can study math at Georgia Tech. And so they have a program there in applied mathematics. And so I was like, well, I'll just be a math major. And I just take a bunch of math classes, right? More calculus and differential equations and then abstract algebra and topology and all these wonderful math things, right? But eventually, as I took more and more math classes, I realized that the mathematics was becoming more and more abstract, more and more away from reality, okay? And I was like, I don't really enjoy this. I don't really enjoy just the pure math. Now, there are people who do that and love it, and that's fine, great. And I've read about it, and it's kind of interesting. But I just didn't want to do that for my whole life. And I also didn't want to be a computer programmer, because that was a big thing when I was in school, was that we had a lot of computer programming, and a lot of people were majoring in computer science. But at the time, I thought that was like just programming, right? Writing code. And I was like, well, I don't want to sit around in front of a computer and write code all day. So this degree program I was in at Georgia Tech, it was applied mathematics, right? I think Amy mentioned that, right? Applied math. Well, that turned out to be great because it was applied math, they forced us to take courses in something besides math, right? Taking all these math classes, and they said, well, you have to take something besides math. So you have to go and take something else. So I looked in the catalog. I looked in the catalog and I looked at all the different majors besides math, and I realized that the one that was most like math was industrial and systems engineering. And Amy mentioned that I'm a member of IISE, that's the Institute of Industrial and Systems Engineering. And I was at Georgia Tech, which has a very good industrial and system engineering program. And all I knew about it was that they had these classes in operations research. And operations research is the use of mathematical models and mathematical equations and formulas to improve operations. Right now, operations is a big word. It means a lot of different things. It means buses, it means transportation, it means factories, It means all kinds of different things, okay? And that's what I wanted to do, because it was like the application of mathematics to real world problems. And that's what I was more interested in, real world problems. So I went and took all the operations research classes at Georgia Tech, and I really loved them. And I was like, well, I want to do more of this. So I decided to go to graduate school, and I was very fortunate to have that opportunity. And I decided to go to the University of Florida because I thought they were doing some interesting research in manufacturing and operations research, and that's what I wanted to do. So I went back to Florida, and it was a wonderful time, and nice and warm. And then I got my PhD, and I was looking for a job, and there was an opening at the University of Maryland in College Park. And I mean, to be honest, it was the only job offer I had. Right? I was looking for jobs, and they were the first people to give me a job offer. I'm like, okay, I'll take it. So even if it means moving to Maryland, and I'd never been to Maryland in my whole life. So sight unseen. But it turned out to be good. And I got a job there at the University of Maryland, and I started working there and doing some engineering work. And then I got a job as a professor at the University of Maryland, and I was teaching engineering, mechanical engineering. Now remember, I was a math major, okay? Now I'm teaching mechanical engineering to college students, okay? Well, what did I do? I did not teach thermodynamics or statics or anything like that. I taught design, engineering design, because design is is the special thing. It's the special superpower, you might say, of being an engineer, okay? Now, I'm going to go off on a tangent here for a little bit by design. Okay, so STEM, right? Science, technology, engineering, and math, right? STEM, okay? Talked about the math already. But I'm going to focus on the science and engineering for a moment. So, any of you ever thought about the difference between science and engineering? You ever thought about the difference between those? No? No? Okay. Well, I'm here. That's why I'm here, to tell you about the difference.
Good question.
Okay. So, traditionally, science is about looking at the real world, right? And describing what's going on, right? Weather, geology, rocks, right? The ocean, plants, the human body, right? All these things that are going on in the real world is fascinating, right? And this is what scientists do. They go out and they study these things in the real world, and they describe what's going on. And then sometimes they do experiments, because they're kind of like, well, what if we did this? What would happen? What would happen if we did this, right? And then they describe what happens, right? Okay, that's science. But engineers design things, right? That's what you're doing here with your robots, right? You're designing robots, right? Now, robots can be used for lots of different purposes, including doing science. Engineers design robots so that scientists can do their science, okay? But the great thing about engineering is that we get to design things, okay? Now, there's a lot of other work, right? You have to build the robots, you have to test the robots, there's a lot of other things that go into it. But the key thing that you're doing as an engineer is you're designing, okay? That's what I would teach, and that's why I still teach that. Well, then I started as I was teaching it and reading about it and thinking about design, what I realized is that the key thing that the engineers do is make decisions. Okay? So now think for a minute about the robots that you're building, right? And think for a minute about the decisions that you had to make in your robot, right? What kind of processor, what kind of wheels, what kind of motor, how to connect everything, right? How to build the structure, what kind of material to use, right? Even how to build it, right? Which tools to use, right? When do you do this? When do you do that? These are all decisions that you have to make your robot, okay? And you have to make those decisions. You have to decide this or that. And eventually, you have to make a choice. You can't do both, right? Either you're going to use this type of wheel or you're going to use that type of wheel, right? Eventually. Now there's a whole process of decision making, And I wrote a whole book on decision making. I didn't bring it today. But what I did bring is a book on meta reasoning. I'll talk about that in a minute. Okay, so decision making is the key thing that engineers do. Okay, scientists describe the world, but engineers decide about what things should be. They design what things should be. Okay, so that's a key thing to keep in mind. If you prefer to go out into the world and describe what's going on, look at what's going on, then you're probably maybe you want to think about going into science. If you prefer to design things and make decisions about that, and then see those things become reality, then you might want to think about going into engineering. Okay? Okay, so there's a little career advice there for you. Okay, where was I? Oh yeah, right. So I'm teaching design and decision making. And then I had an opportunity to do a sabbatical. Sabbatical is a great thing for a professor because it gives them a chance to like stop teaching for a little while and sort of go back to school. Okay? Now you're in school now, right? And you probably are looking ahead and you're thinking, oh, I have many, many more years of school, right? Got to get through middle school and high school, and then I got to go to college and get through all the more years of school. And maybe some of you are thinking you'll go into a profession where you want to go to graduate school. And you're thinking, oh, all these years of school, when am I going to be ever done with school? Well, I can tell you, you will be actually done with school someday. But you will never stop needing to learn things. Okay? Lifelong learning is a real thing. Okay? It's certainly true for me, and it's certainly true for all my colleagues. And you just always want to learn new things, right? Technology's changing, and there's just always more to learn. Okay? And part of that's just because, being curious, but part of that is important, right? Because if I'm going to teach my students to be successful, I need to learn things that I can teach them, right? Okay, so being on sabbatical, I get to learn new things. I learned about meta reasoning. Now I'll take the book.
Yes.
Okay, so this was 2018. Now, 8 years ago, I started my sabbatical, and I started looking into meta reasoning. And eventually, I'd done enough reading and done some work on my own, and I wrote a book about meta reasoning for robots. Meta reasoning is a branch of artificial intelligence. I'll pass this around. Okay. Meta reasoning is reasoning about reasoning, right? That's why it's called meta reasoning, right? Because it's thinking about thinking. Okay. Now we as humans, we do this like subconsciously. We don't think about meta reasoning. We just kind of do it. Okay. But for robots, as you know, anything you want a robot to do, you have to program it, right? You gotta tell the robot exactly what to do all the time, right? It can't think on its own. Right? It's just running whatever code you wrote. It's the same thing for meta reasoning. We have to write programs that tell the robot how to meta reason. Well, what does that look like? Well, that might be like fault detection, right? Like the robot's going along and it has some algorithm that it's using, right? And it for whatever reason, the algorithm fails. Like it can't find a solution. Well, then you need a meta reasoning that can detect the fact that the program failed, and then the meta reasoning can do something about that, right? It can rerun the program, or maybe it runs a different program, or maybe it just tries something else altogether, okay? But meta reasoning gives a robot the ability to think about its own thinking, okay? Which means you're not stuck with one thing. It means it gives the robot more flexibility. So when it gets into more complicated situations, it can be successful, even though it's more complicated. And so we've been doing work on meta reasoning now for a number of years. That's what led to the book. And I've had the opportunity to collaborate with many great people on meta reasoning research, okay? And we're still doing, and I'm doing meta reasoning research now at the Catholic University of America. As Amy mentioned, I'm a professor there in the Department of Mechanical Engineering, and I have a lab. It's probably about the size of this room, and we've got some robots there that we're working on. We had a couple of small yaw boom transbot robots that look like little tanks, because they got treads just like tanks, and they're green, just like tanks. They're not tanks, but we had those, and we have those still, and they operate using the robot operating system, and they can do autonomous navigation. And we did some meta reasoning research with them. And right now, yeah, there's a train spot. Yep. We didn't put the fancy arm on the front. We weren't too worried about that. We just drove it around, and it learned to drive itself around. And now we have a robot called a Leo rover. It's a little bit bigger than that. It's got 4 big wheels. It kind of looks like the kind of thing you'd see on the moon or on Mars. So that's why they call it a rover. And we're busy putting that together, and that. But let me back up a second now. So anyway, that's about meta reasoning. And as I encourage you to, as you move forward in your robotics careers, to think about how meta reasoning might be useful to you. And I'll be happy to share my wisdom about that with you. But let me back up for a second. Because I told you I started in mathematics, right? Math is just like writing equations, right? You solve problems on paper and pencil. I love that stuff. Word problems, I love word problems. Best thing ever, word problems. And but when I first started working with robotics, I was working with other people who had the robots, right? But then one day I was doing a project and we had our own robot. Yeah, actually, why don't you bring up the clear path of Jackal?
Yes,
Can you find one of those? And we had a clear path Jackal, and it's it'll fit on that table. It's not that big, but it's small enough to run around inside. Well, then we had a clear path Jackal. Now here I am. I have a couple of college degrees. I've been teaching at the university for 20-something years, and I now have my first robot. I had no idea what to do with that robot. When I first started, I didn't even know how to turn the robot on. Yeah, this is the Jackal. They can move pretty quickly, and they can go outside. But I knew nothing about robots. Now you guys know more about robots now than I did back then, okay? And some of you probably know more about it than I do now, okay? Because I'm still not like the robotics expert, right? I mean, I remember the first time I had to flash an SD card for a Raspberry Pi. I was like, what does that mean, right? I started by knowing nothing, okay? But I had students and collaborators and YouTube, right? And I figured it out, okay? So the point I'm trying to make is that in robotics, just like in any other field, right? You start by knowing nothing, right? And you just have to keep learning, right? And so eventually you'll finish with school, but you'll never stop learning, right? Because there's always something new to learn, okay? So that was my first experience with robots, being basically like totally lost because I had no idea what I was doing.
Professor
But I
Herrmann,
eventually
when
got it.
did you start to explore the robots? At what time did you start?
Well, the first robot I had in my lab was when we started the collaboration with the Army Research Lab.
Oh, okay.
So around 2020. So, and that was a little bit after I'd done the sabbatical. Okay, so now bring up search for CRFC, and then football. That should do it. And yeah, that right there.
This one?
So now at Catholic U, we have a group of students who are building robots for collegiate robotic football. Okay? And these are little robots, 16 inches square. They would probably fit right in one of these squares right here on the floor. And they are remote controlled, right, with game controllers. And they have 8-on-8. It's 8 robots versus 8 robots playing football with little footballs. I don't have one with me today, but the little footballs are about the size of these little purple balls, right? And they have, yeah, you can see one there.
It's very cool.
And they play football. They try to get a first down, they try to score touchdowns, they try to kick field goals. And the court is about the size of a basketball court, okay? And it's usually played in the gym, right? And they mark off the lines and
So
everything.
these
There you
are
go.
teleoperated.
Yeah, they're all teleoperated machines.
Same as the FTC competition, right?
Yeah. Yeah, so we have a group of students at Catholic U who are designing, right, their engineers are designing, and then building and testing robots to compete in the tournament. The tournament's gonna be in April, up in Ohio, so we'll drive up to Ohio. And, I don't know, we'll see, this will be the first year that we've competed, so we'll probably lose really badly. But we'll learn a lot, and then maybe next year we'll do better.
So
And
is this like a state level competition? Other universities have
it's a competition between universities around the country. Most of the universities involved are in the Midwest, like Purdue and Notre Dame, Ohio Northern, but there's a few in other places, like in Maryland. So, in our lab, we've got the students are working, just like you guys are working here, right? They're working to design their robots and build them. They've got to cut out the parts and put them all together and integrate the motor controllers and everything like that.
Very nice.
So, you guys have any questions about robot football?
Do the robots communicate with each other, or?
Not at this
Really
point,
That's a very
not at this
good
point, but maybe in the future,
Yeah.
the robots can
In
communicate.
fact, Professor Herrmann, one of the big research was on the multi-robot
Yes.
communications. Yes, so
Yes,
that
I've
would
worked
be
on-
something that if you can talk about that, because what they're doing, the students and FTC competition, they are actually competing with each other, but they are not communicating with each other. There are
Right.
4 robots, 2
Right.
teams, and humans are communicating with
Right,
each other
right.
to just kind of do the coordination and teleoperating. Initially do some autonomous, like for how
Yeah,
many?
30 seconds
30
autonomous.
Yeah,
seconds,
right.
but then start teleoperating.
Yes, yes. So multi-agent or multi-robot systems is a big field of research. There's technical challenges, getting the robots to talk to each other through some kind of radio, right, or Bluetooth signal. But then there's like the more like intelligent part of it, like how do you get them to allocate tasks? Like if you put a bunch of robots in this area and told them to pick up all the balls, like how would the robots decide, well, this robot's gonna go over there, and one robot's gonna go over there. The robots would have to figure that out intelligently and autonomously, right? Instead of having a human tell them where to go. So I worked on algorithms that the robots can use so that the robots themselves can figure out which robot's gonna go where and do what. And there's a lot of interesting research in that area, and there's some meta-reasoning problems as well. So, yeah, so that's multi-robot systems. That's the next thing up. It'd be great to have autonomous robots here communicating with each other, but they don't do they don't do that right now. So,
You call them multi-agent, is it?
multi-agent?
Yes.
I was just trying to get you to call.
I had a question about robots.
Anyway, I'll be happy to answer any other questions.
I had a question about the robots that are playing football.
Yeah, the football
So,
robots.
When you're saying, I was reading your book a little bit, meta reasoning, they make logical choices, and they consider time, they consider other tasks, like, just using what they do in the game. Could you give me like an example of where they make a specific choice, a reason? Because I'm just curious how they do
Yeah.
that. Like that's really, I know it's complex, sounds like it, but. Is there
Well,
some-
okay, so the state of the art in collegiate robotic football is teleoperation, right? So there's a human controlling the robot directly and using the game controller to drive it around, just like you would drive around a robot in a video game, right? It's like playing a video game, but in real life, right? So that's what's the state of the art in robotic football, okay? But we have other robots in my lab that can operate autonomously, right?
Okay, autonomously.
Autonomous behavior means that the robot is deciding what to do with no human telling it what to do. So the robot decides how to pick up the walls, or it decides how to move around the building without running into things, right? It can do all that on its own. It doesn't have to be driven, right? NASA just recently announced that they had the Mars rover had done some autonomous driving on its own. It had come up with its own path. It had come up with its own waypoints and followed those. Now, as you know, Mars is a long way from here, right? It takes a long time for the signals to go back and forth between Mars and the Earth. So the robot usually drives autonomously, but it follows the directions of the human on Earth. But this experiment, they let the robot itself figure out what to do. So the robot was making its own decisions. And they hope to do more of that in the future because it would make life easier for the operators, it would make the robot more efficient and things like that. So that'd be kind of like an example of like the state of the art in robots on Mars, right? Those rovers on Mars are just robots, right? And they're basically teleoperated. Anyway. So what questions do you guys have? Any questions for me? Yes, in the back.
For the robot football, are there any limitations to the robot? Like, can it like not expand or like size limitations?
There are limitations on its size. There's if you saw one of the videos, there was a center robot that would pick up the football and hand it off, so it's allowed to extend an arm. But in general, the robots have to kind of stay compact. There's no stiff arming in robot football. Yes?
How are you like down?
Yeah, so that's a great question. So they have in the past, they tried to use a tackle sensor, which would basically be like an accelerometer, so that if the robot carrying the ball ran into a defender robot, the defender would hit the ball carrier, and that would trigger the tackle sensor. But they realized that doesn't work very well because the ball carrier is always running into its own robots, to its teammates, you might say. So now there's actual humans, right, who are the referees, and they just watch, and it's basically touch football at this point. Because as soon as the defender touches the ball carrier's down. In the back there.
I have two questions. One, do they ever like get broken when the robots hit each other?
Yes, all the time. That's a major problem.
And also, have you ever driven one?
Yes. It takes some practice to get the hang of it because the way the motors spin and everything. It takes some practice. But yeah, I've done that.
And when the robot like breaks down in the middle of a game, like how do you deal with that kind of?
Well, I mean that's why it's important to have substitutes, right? Just like on a real football team, right? You've got the backups who come into the game when the starter player is injured or tired, right? So they take the broken robot off the field, they put in another robot, and then on the sidelines, the students are working on the broken robot and trying to fix it, right, in real time. So you have to have people, it's like trainers on a football team, right? You gotta have people on the sideline who are there to fix the broken robots. But yeah, they crash into each other, it makes a big mess.
Are most of the plays running plays? Because I imagine it must be hard to coordinate throwing a football and catching it.
A completed pass is like a big event, right? It's very rare. The rules have incentives for making passes, but it's very hard to complete a pass. I think last year there were eight teams, and only one of them completed one pass. It's very hard. Most of the plays are running plays. That's why having really fast robots and having humans that are really good at the game controller is very valuable. So if you are really good at video games, maybe your future's in robot football.
We have a lot of expertise in both coding and actual robotics.
Good.
You said there's like for passing plays, like there's like incentives and also like it's really hard. Like,
Yeah.
How did they actually complete that?
So they have a quarterback robot, and the typical way they do it is the quarterback robot has 2 spinning wheels, right?
Okay.
And then the human operator is is positioning the quarterback robot to point in the right direction. And then there's a wide receiver robot, which usually has like a net on it or something, like netting on it to catch the football. And then the wide receiver robot is being controlled by another human, and usually the wide receiver just kind of like parks there, and then the quarterback robot, the human tries to aim the quarterback robot right at the wide receiver robot, and then pushes the button, and the football shoots out. It takes a lot of practice, and like I said, it's very rare to do it during the game, because the defenders are doing the same thing. Defenders are in the way, everything's moving around. Yeah.
Is there like a center? Like, did they snap the ball?
That's another technology challenge, but they do have, some of the teams have a center where there's like a little arm that goes down, picks up the football, and then hands it off to the quarterback behind the center. It's not very reliable because that arm, as you guys know, right, any kind of robotic arm is hard to do correctly, make it reliable every time. And but some teams have done that. So yeah, that's the idea.
You said something about there being field goals. Like, do you guys have like a leg that's strong enough, or did you have to do any engineering to get around like the size and restraints?
So the teams are allowed to have specialized kicker robots, and those robots have some kind of mechanism, either a big motor or sort of like a spring-loaded catapult kind of thing that will move the kicking foot down and kick the ball. So if you go on the website, you can see, not here, but you can see examples of that. If you look at some of the videos, yeah. So they have kickers too.
So our robot actually has 2 spinners that launches the balls into the basket.
Okay, yeah,
on that
same
one.
kind of idea.
Just imagine having to
Yeah.
coordinate with another robot to get it in the right place to catch it.
Right.
That's
Yes, that's why it's hard. Now you can see in this video, some of the players, the humans, are behind the line of scrimmage. These are on the offensive side. So they're allowed to be kind of behind the line of scrimmage so they can get a better view of what's going on. All the other game operators are on the sideline. So again, that makes it hard to do as well, right? Because you don't have first-person view for everybody. It's quite interesting to go and see the games, and you can hear the robots crashing into each other. So if you're not doing anything in April, you can go to Ohio and visit the Collegiate Robotics Football Conference tournament.
I have a more broad robotics
Yeah.
question. So I was reading that one of the reasons AI has developed so quickly because of the availability of large language models and all the written word that's in databases.
Yeah, that's
And that one of the holdups for robotics is not having a large movement model, they called it this article, or some ability to say, this is how you do this task, or this is how you do that. Do you see that developing, or do you see some other way of building that sort of knowledge for robotics?
I mean, that's an active area of research, right? People are taking videos of robots doing things and trying to put them into generative AI models to do these kinds of things. This NASA example I just mentioned uses a visual language model as part of its technology. I mean, people have been successful with it. I'm kind of on the fence about whether or not that's the best way to do things, but I guess because I'm an old school operations research guy. I like an algorithm where I can see what's going on in the algorithm, right? You have the inputs, you do some calculations, you get the output, in a more traditional sense. But yeah, I mean, it's an open question of how successful they can be. I mean, there's a lot of interesting things going on in robotics, right? I mean, there's humanoid robots, people are developing humanoid robots. But I think an important thing for robotics to consider is once you get beyond like robot football or exploration, when we start having robots like here, like in our lives, like in our homes and in our workplaces and at the store and places like that, we need to think about like how we interact with the robot, right? Because now we're like talking to a machine, right? And it's very important for us as engineers. We always have to keep in mind that robots are machines, right? We can program them, they can do really cool things, but they're just machines. They're not actually people, and they shouldn't be used to replace human-to-human relationships, right? You can't have a relationship with a robot, right? It's just a machine, right? Like your toaster, right? Or your car, okay? Now, it can do really cool things, and that's fun. But you can't have a relationship with a robot. So it's important for us as engineers to keep that in mind, right? We design robots to do certain tasks, and we want them to do the task very well, but we don't want to have robots that replace relationships, right? You have relationships with your parents and your siblings and your friends, right? You can't have the same thing with a robot. It's just a machine. Okay, I know the robot football is fascinating.
Right.
Now we've gone on to dogs.
I was showing the recent NVIDIA
Yes.
framework with vision language models.
Yeah, the
with
vision language models. It's pretty cool.
humanoid. But you're right. So it still takes a very long time. But
Yeah,
it's there.
yeah, it's pretty interesting what they can do. But I mean, in my book, which is being passed around, like the first paragraph of my book talks about all the ways that robots fail. Right? You guys are building robots, you know how they fail, right? Do all kinds of crazy things, right? So it takes a lot of work to get a robot that's reliable, and that's why the robots that are like really being used in industry and such are actually very simple machines, right? Like robotic arms for automotive assembly. I mean, the Mars rover is pretty sophisticated, but it's basically controlled by humans all the time and monitored by humans. I mean, there's a huge number of people monitoring and operating that robot, right? It's a very expensive robot. But I think it's great that we have so many people, such as yourself, who are interested in robots and learning about robots, because it's going to be an important technology, for the future. And there's just going to be more and more robots. There's no doubt about it. So that's why I'm excited to be part of it. And I guess what I would just say in closing is, if you're ever interested in coming down to see what we have and what we're doing at Catholic U, we're just down the road in Northeast Washington, off of Michigan Avenue, and be happy to show you what we're doing. Okay? But yeah, thanks again for the opportunity to be here. Appreciate Amy inviting me, and for all you paying attention. And I'm glad you found the robot football interesting. I think it's a pretty cool thing myself. And I hope our students are successful this year. I hope you're all successful in your competition. And I hope I can wander around for a few minutes after this, and maybe some of you can show me what you're doing with your robots.